I want to talk about more things with geometric sequences. And I know that we got a little bit cut short in class with our notes. So I want to go back up to number 3 and look at another finite example. And so, make sure my pen works there. Very good. So, and I know it's finite because I can see, right. It doesn't. There's no infinity. It's very countable. And so when I have a finite geometric sequence, remember I can sum it up by saying it's the first term times 1 minus the common ratio to the nth power divided 1 minus the common ratio. And again, how do I know it's geometric? Are you multiplying by a common factor? So if you take a look, I'm multiplying each of these by 1/3. So that's my common ratio. So I know my common ratio is 1/3. I know my starting term is 3 because that's what I see. So I'm going to have 3 times, and it'll be 1 minus 1/3 to some power. I have to figure out how many I have of these, divided by 1 minus 1/3. Now, on first inspection, you might think, oh, there's 40 numbers because that's my highest exponent. But you have to think about like you really aren't starting at 1/3 to the first power. This right here, that term is 1/3 to the first power. Then the next term is 1/3 to the second, right? 1/3 to the third. So really, if that term that this right here, 1/3, that's not the first term, that's actually the third term. So I've got really 2 more terms here. In other words, I actually have 42 terms that I need to worry about, because these are the first 40 terms, and then here's 41, and here's 42. Another way you could think about that is 3 is the same thing as, 3 is the same thing as 1/3 to the -1 power. So you have from the -1 power all the way up to the 40th power. If you wanted to count how many there are, you do 40 minus -1, which is 41. And then remember, those are the spaces. You add 1, so there are 42 numbers. So this technically is an answer. We could clean it up a bit because I know 1 minus 1/3 is 2/3. So we can say it's 3, 1 minus, sorry, my pen. There we go. Let me try this again. 1 minus, it's been a while since I've used my keyboard here. 1/3 to the 42nd power. And then all that's divided by 1 minus 1/3, which is 2/3. And certainly you could multiply it up to get 3 times 3 is 9/2. And then you could say that's 1 minus the quantity 1/3 to the 42nd power. Now that's a really, really complex number or cumbersome number to express, but we can just leave it like that, and that should be 42. It looks a little bit like 92, so let's just make it a little better so I can sleep tonight. 42. Okay. So you do definitely need to know this formula, right? That's finite. And we talked about in class end of the period today that the sum of an infinite sequence, an infinite geometric series, is this formula, a over 1 minus r. Now there's a few constraints, and for some reason I didn't clip them into my smartboard, but you have them in your notes, that the common ratio, we said this only works when the common ratio as an absolute value is less than 1. Because we want our terms to be getting smaller. If our terms are getting bigger, like if my geometric sequence is 1, 2, 4, 8, 16, 32, 64, that's definitely geometric. So if I would express it as, k equals 1 to infinity of 2 to the k minus 1, yeah, that's an infinite geometric series. But the problem is, since the ratio is not less than 1, your terms are getting smaller. And if your terms are getting smaller, we can't possibly add them up. So if you have a ratio that's bigger than 1 like this, we would say it's an infinite sum, because its value doesn't approach anything. It approaches infinity, right? So we are only looking for, if I could draw infinity, we are only looking for geometric series whose ratio is less than 1. And it could be negative because it could alternate between negative and positive, and that's fine. And we also want to make sure that our ratio is not equal to 0, because if our ratio is 0, that means you multiply each term by 0 to get to the next term. So no matter what you're starting with, right? Think about that. If you started with the number 3 and multiply by 0, and multiply by 0, and then multiply by 0, you have a pretty boring geometric series because it's like non-existent, right? It's just the number 3. Okay, so example 3 looks at ways we can represent infinite geometric series. If it's given in terms of terms, like these first two I see. So like you see this like ellipsis that goes on forever, right? So that indicates the pattern goes forever. So we know it's infinite. And you need to check, is it a geometric ratio? So how do you get from 6 to 2? Oh, you multiply by 1/3. How do you get from 2 to 2/3? You multiply by 1/3. So I've definitely identified that my common ratio is 1/3, and my starting term is 6. It's infinite. It's a geometric series. Its ratio definitely, right? Our ratio is less than 1. So I now can apply the formula A over 1 minus R. And so then my A term is 6, and my ratio is 1 minus 1/3, which is equal to 6 over 2/3, which is, you could multiply by the reciprocal. I'll show that there. That's 18 over 2, which is equal to 9. Okay. Part B, it's another geometric ratio. I know that because I'm multiplying by almost 1/3 is actually negative 1/3. My ratio is negative 1/3. And that still fits the definition. We're looking for a ratio in absolute value that's less than 1. We want our terms to get smaller, and that definitely fits. And my first term, a sub 1, is equal to 9. So I once again can apply my formula A over 1 minus R, and my starting term of A is 9, and then my common ratio, be careful, it's negative 1/3. So I have to subtract that from the bottom. So then that's 9. I realize my A and my 9 sort of look alike. 1 minus a negative 1/3, which is 4/3. And then that can flip up to 3/4. So it's 9 times 3/4, which is 27/4. So there's my sum for that. Now, part C. Be careful, because look at your common ratio. Your common ratio is negative 2. And even if you like right away, I should know, oh, not possible, right? This actually, there is no sum. It actually diverges because it oscillates back and forth between a very large positive and a very large negative. So again, if you start thinking about the number line, it's like, well, if here's 0, first you add 1, and then you add negative 2, and then you add positive 4, and then you add negative 8, and then you add positive 16, and then you add negative 32. Because you're going back and forth, and each time you're going farther and farther, that's why we say it diverges. That's a bit different than an infinite sum. If all of the terms are headed in a positive direction, then that's how we know you have an infinite sum. If the terms kind of bounce back and forth between positive and negative, we say that sum diverges. Now, like you might get into tunnel vision and just say, hey, my ratio is negative 2, and I get A. See, look at my pen doesn't even want me to do this because you can't. A over 1 minus R. Well, even if I try to algebraically get an answer, 1 over 1 minus negative 2, which is 1/3, that doesn't make any sense whatsoever in this context because my numbers are oscillating between a very large positive to a very large negative. And so having it balance 1/3 makes no sense whatsoever. So if you just write not possible, I would definitely accept that. But I want to show the difference between all the terms being positive and getting really large, or oscillating or alternating back and forth. Now, you can definitely have alternating sequence like part B, right? That was fine because his ratio was less than 1. Okay, part D. So that one is geometric, and how do I know? Because every term you're multiplying by 1/10. So you have a common ratio, and as an absolute value, that's less than 1. So you know we can apply A over 1 minus R. That first term is 100. and then you divide by 1 minus 1/10. So that's 100 divided by 9/10, which is equal to 1,000 divided by 9. Okay. And then I know there's two more examples, part E and part F. You could certainly pause the video and you could try them. These are given in sigma notation. And when you're given in sigma notation, it's very easy to see. I think they're geometric because you can see what kind of function, and you can see your ratio, 1/2 to the k, 1/4 to the k minus 1. So we definitely know it's geometric. Each of the ratios are less than 1. So we just have to make sure we can identify what that first term is. And when you're not quite sure, just look at this lower index and just let k be 1. If you let k be 1, our first term, our first term would be 1/2 to the first power. Oh, so it's 1/2. So then I still can follow my formula, a over 1 minus r. So the first term is 1/2. 1 minus just happens to be that same common ratio. So that's 1/2 divided by 1/2, which we know to be 1. That's kind of cool. I mean, think about what you just added up. You just added up the powers of 1/2. So 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32. And basically, you would get a whole number, a 1. And that's exactly what we did in class yesterday. We tried to get out the door, and you only go half the distance. Well, all of your parts will add up to the whole distance, but you'll never, ever get there. Okay. And then part F. Might as well finish out the notes here. So part F. So same idea. I know it's geometric. I might want to just double check what is our first term. So that's 12 times 1/4 to the 1 minus 1 or 0 power, which is 1. So our first term is 12. So now we can apply our formula, a over 1 minus r. That's 12 over 1 minus 1/4, which is equal to 12 over 3/4. And then we can flip that around. So it's 12 times 4/3. 3 goes into 12 4 times. 4 times 4 is equal to 16. Fantastic. Okay, so that is kind of like a refresher into geometric series. Make sure you're watching that common ratio. I will certainly try to test you on that, trick you on that, if you will, to make sure that common ratio is in fact less than 1.